Dear all, welcome to Om Learning Classes. In this lecture, we are going to learn the basic parameter of the frequency modulation. So, as per the definition of frequency modulation, it is the type of angle modulation in which the instantaneous frequency of the carrier signal. I mentioned the instantaneous frequency of the carrier signal. This is very important. Is proportional to the instantaneous amplitude variation of the modulating signal, which is also known as baseband signal, while keeping the amplitude of the carrier signal constant. So, as per the basic parameter of the frequency modulation of FM, first we consider the frequency deviation. As per the definition of frequency deviation, the instantaneous frequency of FM modulated signal, very important. Now I consider FM modulated signal. FM modulated signal means after frequency modulation. The instantaneous frequency of the FM modulated signal varies with time. That is known as the frequency deviation. And it can also further define that the maximum change is in the instantaneous frequency on either side from the unmodulated carrier frequency omega c. Means before modulation we have the frequency that is unmodulated carrier frequency omega c, and after frequency modulation it can be increment in omega c or it can be decrement in omega c on either side. I mentioned on the either side. It can be increment and it can be also represent decrement. So, if it have the variation and that variations in that range, that is known as frequency deviation. So, as per the mathematical representation, the frequency deviation is defined by the magnitude and sign of kf-mt. We know what is kf. Kf is your frequency sensitivity factor and mt is your modulating or baseband signal. So, as per their magnitude and as per their sign representation, we have the increment as well as decrement in our unmodulated carrier frequency, that is omega c. So, as per the mathematics, we have to calculate the omega I, which is known as instantaneous angular frequency of frequency modulated signal, and omega I is equal to, it is the derivative of total angle of FM modulated signal, that is derivative of theta I t, and that is equivalent to, if we calculate, that is equal to omega c plus kf into mt. And if we want to represent this mathematically representation in the frequency domain or in that is in angular frequency, omega c and omega I, and if we want to convert in frequency, then omega I is equal to 2 pi fi and omega c is equal to 2 pi fc. But the unit of the kf is very important here. So, in the first case, I take both the consideration. In the first case, I will take the kf unit, that is in radian per unit of modulating signal. So, first by considering the unit of this kf, I get the fi, that is equal to fc plus kf by 2 pi into mt. This is the first representation in which we have the consideration of kf as unit radian per unit of modulating signal. So, now we have the consideration of peak frequency deviation by considering the unit of kf as radian per unit of mt. Now, as per the frequency deviation calculation, we get the omega I, that is equivalent to this omega c plus kf mt, or you can say the fi, that is equivalent to fc plus kf by 2 pi into mt, and where the unit of kf is radian per unit of empty signal. Now, if we want to find out what is the value of peak frequency deviation, and that can be in the form of delta omega or in the form of delta f. If it is in the form of delta omega, then unit is radians, and if it is in the unit of delta f, then the unit is hertz. So, as per this fundamental and by considering the unit of kf as radian per unit of mt, we found that this factor is maximized for getting the peak frequency deviation. So, the peak frequency deviation we can get that is of maximum value of kf into mt. And similarly, we can get that is equivalent to kf by 2 pi into mt, their maximum value. And both the representation are there when the unit of kf is radian per unit of mt. Now we take the consideration when the unit of kf is hertz per unit of mt. Now here in this we can find out the fi, and we consider the unit of kf is hertz per unit of mt signal, and with this we can get the value fi that is equivalent to fc plus kf into mt. The mathematical representation is same, that is the derivative of total angle of frequency modulated signal, and with this we can get the value of peak frequency deviation. Very important, if the value is in radian, then kf by 2 pi is there into mt. When its unit is in hertz, then that is equivalent to kf into mt. So this is all about the first parameter of frequency modulated signal, that is frequency deviation and peak frequency deviation. And I consider both the case for getting the exact difference between the unit of radian or hertz. Now, after getting the mathematical representation, we have some another important things are there that is related with frequency deviation. The first thing we have, that is maximum frequency of the FM signal, and the maximum frequency deviation that is equivalent to fc plus delta f, means that is increment in unmodulated carrier frequency. Second, we have the minimum frequency of the FM signal, and that is equivalent to fc minus delta f, that is corresponding to decrement in unmodulated carrier frequency. And by utilizing the maximum frequency and minimum frequency of FM signal, we have another term that is known as carrier swing, and that carrier swing is your f maximum minus f minimum. And if we put the values of f maximum and f minimum of FM signal, we get the total carrier swing of the FM signal that is equivalent to 2 delta f, and that unit is in hertz, means the twice of the frequency deviation is known as the carrier swing in the FM signal. Now, all these three parameters are represented by considering a carrier swing diagram. Now, after this mathematical representation, we have the diagram representation related with f maximum, f minimum and carrier swing. Now, first we consider the unmodulated carrier frequency, that is your fc, and by doing the increment of frequency deviation that is equivalent to delta f, we get the f maximum. So, fc plus delta f, that is equivalent to f maximum. Similarly, we have the decrement in the unmodulated carrier frequency by considering the frequency deviation, that is delta f. So, fc minus delta f, that become equivalent to f minimum. So, this is corresponding to f minimum, this is corresponding to f maximum, and this is the representation of unmodulated carrier frequency. And the F maximum minus F minimum is your carrier swing, and that is equivalent to 2 delta F, or you can say twice of your frequency deviation of the FM signal. So this is the graphical representation as per the fundamental outcome of frequency deviation. Now, as per the concluding remark of frequency deviation, the frequency deviation is useful parameter for determining the bandwidth of the FM signal. That is very important. The bandwidth of FM signal is calculated by considering this parameter, that is frequency deviation. And we have an important consideration related with frequency deviation. The frequency deviation delta F is proportional to the amplitude of modulating signal. Very important point. It is corresponding to amplitude of the modulating signal, because the delta F is equivalent to Kf into Mt, and Mt is corresponding to amplitude of modulating signal and is independent on the modulating frequency. Because it is very important. Why? Because when we consider the frequency modulation, we can take the interpretation that is in terms of frequency, but in actual, the delta F is corresponding to instantaneous amplitude variation of modulating signal, and it is independent on the modulating frequency. With this consideration, we complete the explanation about frequency deviation, which is the basic fundamental parameter of FM signal. Now, in next lecture, we have the another parameter, that is frequency modulation index. So, thank you very much for watching and subscribing Om Learning Classes. Thank you for your precious time. Stay healthy and enjoy smart learning. Thank you very much.